Welcome to this Bright Numbers video. Imagine the following mathematical problem. A bead is sliding without friction along a two-dimensional track, from a given point P, to another point Q, which is situated below P, but not directly underneath it. The bead will take some time to accomplish its journey from P to Q, while it is moving purely under the influence of gravity. A natural question to ask is, how should we design the track, in order to minimize the travel time for the bead? In other words, we want to find a curve that is Brachistochrone, which is Greek for shortest time. Obviously, the curve shown here is a random example and not the solution. It is this Brachistochrone challenge that was posed by the mathematician Johann Bernoulli in 1696. He allowed 6 months for solutions to be sent in, but after this period no one had responded yet. Then, extending the deadline to 1.5 years, Bernoulli received answers from 5 famous mathematicians at the time, amongst others, his brother Jakob, Gottfried Leibniz and Isaac Newton. 2 intriguing anecdotes are worthwhile mentioning here. First, although Johann Bernoulli found a solution, just as his brother, it turned out that the derivation was incorrect. He then apparently tried to copy Jacob's solution as his own, an indication of the jealousy and rivalry that troubled the so remarkable Bernoulli family, with its 8 mathematically gifted members. Second, the story goes that Newton one day found Bernoulli's problem in the mail. Annoyed by the pestering of foreigners on mathematical issues, he took up the challenge and worked overnight to find a solution. He did so and sent it anonymously to Johann. The latter though, upon reading it, recognized its author and exclaimed, "Tanquam ex unge leonum," Latin for, "We know the lion by his claw." The solution of the Brachistochrone problem requires some sophisticated mathematical tools, that were actually partly derived by the mentioned mathematicians while working on it. These include calculus of variations and optimization techniques. In the end it can be shown that the necessary curve for minimizing the travel time is part of a so-called cycloid, which properties we will discuss next. This outcome is non-trivial and somewhat surprising. At first one could have imagined that maybe a straight line would be the answer. The animated example here shows a comparison between the cycloid solution, a straight line, and a vertical drop. We see that the red object, sliding down the cycloid, is indeed the winner. Now, a cycloid is an interesting type of curve in itself, that appears in many different contexts, for example in the study of a rotating wheel. If we fix a point on the outer rim of a rolling wheel and follow its trajectory in time, then the resulting curve is a cycloid. This cycloid is parametrized by using a dimensionless time variable and is expressed in terms of the trigonometric functions cosine and sine. The overall size of the cycloid is determined by the radius of the wheel, r. In the animated example shown here, the origin is placed at the floor and we assume that the monitored point is there at time 0. The second time that the fixed point hits the floor happens at a distance equal to 2 times pi times r, which follows from a simple calculation. This distance between the 2 touching points thus equals the cycloid branch width, as can be seen from the animation. Applied to the Brachistochrone problem, we then have to design the cycloid such that it intersects the starting and end points P and Q. This leads to a unique solution, given any P and Q. Let's check this. First introduce a coordinate system, such that P is on the y-axis and Q is on the x-axis. Then, the whole geometry of the problem can be described by 2 variables, which are interpreted as the overall length, L, and height, h, of the system. The earlier cycloid curve can be adapted such that P and Q are both on it, using a coordinate transformation and write equations that hold in P and Q. The ones for P will eliminate the auxiliary variables x and y. After that, we have a cycloid that will pass through P. In order to make sure that the curve also passes through point Q, another 2 equations arise. By rearranging and then dividing both equations, a new, transcendental equation for the end time t1 is found. No direct, analytic solution is available, but by applying straightforward techniques, for example bisection, this equation is still solvable numerically. Having found T1, the cycloid radius then follows from one of the original equations at Q. Concluding, given any 2 points P and Q, there is indeed a unique cycloid passing through them, which then constitutes the solution for Bernoulli's famous Brachistochrone problem. As said earlier, the actual proof that the Brachistochrone problem indeed leads to a cycloid trajectory requires some special mathematical techniques. Instead of trying to find such a proof ourselves, we wonder if there is another way to approach the given problem. A more practical, intuitive way. It turns out that there is. By splitting up the entire problem in a number of smaller ones. Implement a computer script for these and make use of some numerical solving methods. We could refer to this way of working as the engineering approach. The combination of the many simpler problems leads automatically to an optimization problem, which in the end will reveal the overall solution for the best trajectory, in terms of descent time. In a next video we will explain further how to do this. In this second part, a mathematical background will be provided, as well as a practical implementation in Excel. Also a comparison is made to the known solution, namely the cycloids that we have discussed in the current video. This will demonstrate the feasibility of our engineering method. We hope you liked this video. Please leave a comment. See you in the next one. This is Bright Numbers.